the resistance and reactance of a transmission line is equal. At what power factor regulation is 0? The options are given as 0 power factor and 0.707 lag and 0.707 lead and unity power factor. And the first and foremost thing we have to observe is here. So the regulation is 0 means, that means there is no voltage drop present in the line. So this is possible only when the power factor is leading. So we can directly go for option here C, because no other power factor is leading power factor here. So only one option is given here, that is option C, that is the leading power factor. And this is I mean some of the questions we can we can answer with the help of our common sense, and some of the questions really require mathematics. But this type of questions, if you have a common sense, directly we can go for option C. Anyway, we will solve this problem with the help of numericals, but directly we can select option as C here, right? So if you go for the numericals, and the formula for the regulation is, or I can say the regulation is proportional to I2 R2 cos theta 2 minus I2 x2 plus I2 x2 sin theta 2. This will be plus or minus. This will be proportional to. Okay. So here the plus sign is for lagging power factor, and minus sign is for leading power factor, where cos theta 2 is the power factor, where theta 2 is the power factor angle, so that we can find out the sin theta 2, right? So this is 0 he is saying, so that means what? So obviously R2, if you take I2 common, then we will get R2 cos theta 2 minus x2 sin theta 2 equal to 0. So if you solve this, what we will get? Tan theta 2 equal, that means sin R2 by x2. Theta 2 equal what? Tan inverse R2 by x2. So here he is given that the resistance and reactance of a transmission line is equal. So that's why both are equal. So what we will get here? We will get here 1. So tan inverse 1 means this is the 45 degrees. So the power factor, the formula for power factor is cos theta 2. That is equal to cos 45 degrees. So this means what? This is 0.707. Now what is the power factor? The leading or lagging? It will be obviously leading power factor. So we have to go for option C, and don't go for option B, that is a lagging power factor. So the option here is C.
He has given 3-phase half controlled bridge. 3-phase half controlled bridge means this is 3-phase 3-pulse converter. Okay. In 3-phase 3-pulse converter, the frequency of ripple in the output voltage depends on, frequency of ripple is always equal to pulse number into supply frequency Fs. Okay. Now, frequency of ripple is given as pulse number into Fs. In 3-phase half controlled bridge, this is 3 times of Fs. Suppose if you have 3-phase 6-pulse converter, now what is frequency of ripple here? Is pulse number into, that is 6 into Fs. Okay. Out of these 4 options here, you have supply voltage. This is wrong. Firing angle is also wrong. Load inductance is also wrong. Only answer is supply frequency. Okay. Answer is C.
So here the question is, find out the 3-phase fault current if the pre-fault voltage is at the fault point is 0.97 per unit as shown in the below figure. The circuit diagram is given here, and he is directly given the reactance diagram, right? Generally if you see any questions, and he will give a power system network, and that means what? The power system single line diagram network. So if you given a single line diagram network, then if you ask for 3-phase fault or LG fault, whatever it be, first we have to go for reactance diagram, then we have to find out the equivalent impedance at the fault point, and then we have to find out the fault current. That is the procedure. But he is directly simplified our problem. The problem is given directly the reactance diagram, and he is given the fault point. So our problem is, the simplified here. So first we have to observe here, the fault is occurred at this point, right? So from this point we have to find out the impedance, right? So we have to find out the impedance between these 2 points. So if you find out the impedance between these 2 points, the point J.2 reactance and J.15 reactance is in series, and this combination will be in parallel with J.2. This will be 0.2, J.2, right? So if you find out the equivalent impedance, that is Z equivalent between the fault points, that will be J.2 plus 0.15, that will be 0.35 multiplied by J.2 by J.35 plus J.2. So if you solve this, we will get J.35 and J.2 by J.35 and plus J.2, we will get the value approximately equal to 0.127 per unit. That means J.127 per unit. So this is the approximate value of the equivalent impedance, Z equivalent between the fault points. So right, now after finding this, we have to find out the fault current. So here the fault current is nothing but the pre-fault voltage. The pre-fault voltage generally we will take 1 per unit if he is not mentioned means. So here in this problem he is mentioned a pre-fault voltage, that is 0.97 per unit. So here he is mentioned 0.97 per unit voltage is the pre-fault voltage. So that's why we have to take here 0.97. Otherwise, unless otherwise mentioned, is not mentioned means we have to go for 1 per unit is as a pre-fault voltage. So for a three-phase fault, the equation is, the fault current equation is the pre-fault voltage by the total reactance seen from the fault terminals, right? So here the option will be 0.97 by 0.127. If we solve this, we will get 7.62 per unit, right? So option will be A. This option will be 7.62. Sorry, I have written wrong. 7.62. This is option A. 7.62 per unit. So we have to go for option A. So the important thing is here we have to first observe which fault it is occurred. Whether it is a three-phase fault, then we have to go for a simple reactance diagram. Whether it is a single LG fault, then the procedure is not same as three-phase fault procedure. And we know that the fault current is simply voltage by the fault impedance. So here the fault impedance is given, and that is simply from this diagram. Then after that, just substitution. If you substitute that, we will get the fault current is 7.62 per unit.